For years we've been saying, hey, this function is continuous, this function is discontinuous, right? Things like that. And the only thing about it, the only explanation you've been hearing so far is that, hey, continuous means you can draw the graph without lifting it, right? That's, I highly believe that that's the only way we explain it. See what I'm saying, no? Because if the graph has a hole here, right, that means that in order to draw the graph, you have to lift your pencil and then draw the other piece aside on the other side of the hole, right? And then if it's really smoothly continuous, then you lift and you draw it without lifting your pencil. But we are the math people. We don't want to stay with that kind of naive way of saying it. So we need to come to a real solid and precisely crystal clear definition of what it means by being continuous. See what I'm saying now? All right, so let me point out a few cases. So back from your learning days here, the kind of graph that goes, yes, without lifting the pencil, up and down like that, right? You've seen it? And so at every point on that graph right here, you see, you go through the graph on every point and you don't need to lift the pencil anywhere. So a graph like that, we find that to be continuous, right? I mean, we call that, we've been saying that the graph like that is continuous. And then there are the cases where you run into a graph, right? And then sort of like a vertical line being asymptote here, like somewhere is going like that. And then this vertical line is at some x equals a. And you definitely have to lift your pencil in order to jump to the other piece being asymptotic to that. And so for this function right here, clearly, the reason it's asymptotic right here is because the function itself, right, is not defined. F of A is undefined. Right? So the function is undefined at F of A. So we definitely have to lift up the pencil. We have to lift up the pencil and then further. You can investigate that for a problem like this, the way we're looking at the picture, right? The limits of the function, When we come to that point right here, that limit point A, the limit here fails to exist, right? So there are cases like that. So we recognize. So in this case right here, we're saying that the function is discontinuous. In that picture right here, the function is discontinuous, but then specifically focusing at that point x equals A. So continuous continuity, right now we talked about continuity briefly, but then we narrow our attention down to continuity that's happening at a single point there. Okay, as one singular point. And so there are a few other cases, and we want to, once again, and I brought this up on the earlier lecture, but we want to have a closer look so that we can come up to an actual definition. So there could be time where you're drawing your graph, right? And then see, I point out this kind of graph right here in the earlier lecture right there. But so at some A value, some x equals A, we do have a limit. The limits do come to some value here, but unfortunately we have an empty point here. So in this case here, yes, the graph is discontinuous again, because in terms of drawing it, we definitely have to lift up the pencil to leave that empty hole, to leave out that empty hole right here. So the function is discontinuous at x equals A again. But then what we notice in this case is that the function value at A is undefined. We have undefined value, okay? And then the limits for the function, okay? When x comes to that specific limit point A, is actually some value, some specific value L. Okay? So there are cases it happens like that, and then there are other cases where you have you can have a break in your function. So it looks like in the picture I'm drawing right here, we got more discontinuities than being continuous here. Okay. We have a break line right here, x equals A, okay, and we may have a graph that one piece going up, but that hits that point and the solid point is included, and then we may have an empty point, and then it comes out with another piece right here. So the function is piecewise. So in this case right here, it's another discontinuity that we can recognize. Another discontinuity. But what's happening in here is that the function value is defined. Right? The function value has let's say we put that here as some value C, for example. So the function value at A is defined to be C. Right? It's defined. But then the limits does not exist. X comes to some value A. That limit point A does not exist. And so there are so many different cases for this continuity. Let's do another case of this continuity that, yes, we may have a limit, okay? But then and the function can still be defined as well. Okay? The function can come to a value being defined, and then the limits come to some value. Okay? But this is still this continuity. Okay? And x equals A. What I'm seeing here is the limits for this function. When x comes to the limit point A, is some value L. And then the function is defined at A. It comes out here, the value C right here, where that vertical, where that point is at. But then in this case right here, the worst thing is, the thing I'm seeing, the limit is not equal to the function value. Right. So now we're looking at continuity here, and at that specific point, you can see that the value has to be defined. The limit also exists. We have limits, and then we have the value. And so after those situations we get, now we come to a formal definition. Right. So any function. So continuity that we're studying right now is the property that happened at one specific the x value on the x-axis here. Okay. So a function f of x is said to be continuous at x equals a. Some textbooks say conditions, some textbooks say requirements. I'll go with requirements again. So you can see that number one, definitely, if you're looking back, I want you guys to think about, we can derive the definition ourselves once we are through with looking at the cases here. But you see, the only picture for continuous is here, right? And let's say x equals a is there. So in this case here, being continuous, the function has to have a value right there. See what I'm saying? In order to be continuous at that point. And so the first requirement, in order to say that the function is continuous, the function value, it makes sense, it has to, when you substitute x equals a into the function, it has to be defined. Okay? F of a is defined. So you gotta be able to substitute the value into the function and come out with some output, having a solid point then. That's the first requirement. Okay? And then aside from that, the next requirement is here. When you're looking at the limits for the function, treating a right here as a limit point, and taking the limits of the function when x comes to a right here, more proper way of saying that is this limit, first thing doesn't exist. Okay? And this as a finite value. You can come out with some, when taking the limit, you have to come out with some value, some actual value instead of infinity or the does not exist. So, see, when we're looking at this case, we are picking any point, the function is continuous at that point, x equals a. Okay. So, but we recognize that for continuity, the limits has to come out being a finite limit. It's not like a DNE. Like say in this case, the limit is a DNE. We gotta lift up our pencil right there for that. Okay. Or in this case right here, the limit does not exist. Okay. Right. So that's requirement number two. The third requirement that's important, really important, is that once both of these are satisfied, the limits, even though exist and being a finite, the limits gotta be, the limit that comes out gotta be equal to the function value when you're substituting it. Okay? Think back at what I've been always saying. See, first day when I introduced about taking limits, I've been always yelling out loud that it's not the same as substituting the values in. Because there are actually quite many instances where substituting in the values won't come out, because you may have a function being undefined, but you may still have a limit right there. Okay. So now when we formally define the limits, when we formally define continuity most of the time happens when, of course, after these requirements are passed. Okay? And continuity happens when the limits indeed equals to the function value substituted in. Yeah. Okay. So anytime you have those three requirements satisfied, then we can say that the function is continuous at x equals a. Or the other way around, if you know that the function is continuous at x equals a, these three requirements must have been passed already. Okay, must have been satisfied already. Okay? So right now we focus on being continuous at specifically at one point. Okay? So think about, yes, when you draw the function, you can already notice the function is a lot more than just 1 point, right? And then later on, once you guys are fluent enough with proving the function being continuous at 1 point, we're gonna push that into the function being continuous everywhere. So that's gonna be the concept after that, right? But right now we just focus continuity at one specific point here. Okay. So let me bring in the first example right here. A very common example. We want to determine x squared minus 2x plus 3. The given value right here. We want to determine continuity when x at that point x equals 1. Okay. All right. So getting into this problem right here. See. All we have to do is to make sure, in order to say that, hey, the function continuous or discontinuous, all you have to say is make sure, if you want to say it's continuous, then you gotta make sure that, or point out that it passes all of these three requirements. I'm talking about a function passes three requirements here simultaneously at this given value. See what I'm saying? No? So that's all we have to do right here. So the first thing I'm going to check, right? The function is x squared minus 2x plus 3. Let's say we substitute x equals 1 into the function. Are we going to have a value coming out just easy? Okay? And so being defined means you should be able to proceed all the way to the end and do the calculation. It's not like 1 over x, and when you substitute x, then you got an undefined because you can't divide. Right? That's where it's called undefined. Okay? So for us right here, when x equals 1, will there be any trouble calculating this? There isn't, right? There won't be any trouble. So it will come out as easy as just 1 squared minus 2 times 1. Right? And when you're writing up your work for them, make sure you use parentheses anytime you're doing a substitution. Okay? And so this value comes out being what? So that's making it altogether 4, right? And it's so here I put a check here, meaning because once you can come up with a final output for here, that means your function is defined. See what I'm saying now? So we checked it, and our function has passed the first requirement at x equals 1. Okay. And once we have passed with that requirement, then we move on to the next requirement. Now, right now I'm staying strictly with that order. We check for function being defined, and then the next thing we check for the limit exists or not. So your function here is x squared minus 2x plus 3, right? We want to go ahead and take that limits by letting x get close to 0 over here. See what I'm saying now? I mean, x getting close to 1. And yes, it takes a few steps here. Limit law say, because like I said, right now we're not sure if the two will equal. Substituting in is a different work. Taking limits is a different work, right? And that's why we have to follow through the limit laws here to find out limits. So limit on x squared, subtract limits on the 2x terms, right? And we added with the limits on the constant term. You guys follow it? So now I hope it's becoming more clear. The reason why I keep asking you to show all of your limit law steps, whereas we were not directly doing this, because doing that we only verify if the function is defined. And so the limit laws Continuing further with that, we're looking at the limit of x, right? For that first term, when x comes to 1, right? Square that term right here. This here gives me minus 2 and count, multiply with the limit for that simple function x. You guys following? Right? And plus the limit of the constant of term 3 here when x comes to 1. And this is now the reason why we over to this board right here I'm looking at. So that limit here comes out being so 1 squared, right? Minus 2 times 1 plus 3. So the limit works, after a whole bunch of limit laws are applied in, we're looking at this final setup right here, and that comes out being another 2, right? So this time the limit came out being a finite value. See what I'm saying? Now the limit exists, right? It came out being a finite value. So I put another check right here that the requirement number two for our continuity checking has passed. Okay? It came out, the limit came out as an existing number and being a finite value. So now we're moving on to the third step right here. But then before I move to the third step, you see, checking for a function being defined and checking for the limits right here. These two steps, even though I wrote it here as the order number 1 and number 2 right here, but these two are not really dependent on each other. So you can really swap their order right here. In other words, what I'm saying is you can also start out checking the limit first, and then check the function being defined after. So these two steps right here, the order is not strict. But the third one I'm about to do right here, we want to make sure the limits also come out, that came out also equal to the function value. This step always has to be after these two other earlier steps. Okay? And so now the point now is that we've had two results, right? One result that came in by substituting the value and we got defined, and then one value that's done by taking limits. So now what do we notice? The observation is telling me that, hey, the limit of the function f of x here, right, as x comes to 1, that limit came out 2, right? It also equal to the function value at 1. See what I'm saying? No? So I'm only saying that, in this case, after the observation, we notice that the function's limits is the same as its function value when we substituted it in. And now, after passing the third requirement, our conclusion now here goes, so f of x, right? That's a conclusion. It leads to saying that f of x is what? Is continuous. Continuous, specifically at x equals 1. Okay. Then just doing one problem will never be enough for you to see all the different cases here. So let me bring in another problem in this example. Okay. So how about the next function here, what I'll have on the board here, about f of x squared minus 9 over x plus 3. And we want to find out continuity at x equals -3. Okay. All right, and so it's another function. So now you can see that. Start getting into checking the requirements. First requirement right here, f of -3. Okay, f of -3. Can we really substitute this into the function? Well, it goes -3 all squared minus 9, right? But unfortunately, -3 plus 3 in the denominator gives me a whatever that is divided by 0, right? So this function right here, right now, it fails the first requirement because f of -3 is undefined. So I'm saying now, make a note of that, right? So it fails the first requirement. So now think about it. Once it already failed one of the 3 requirements, is there a need to move on to the other steps? No. Okay? And so now you can just make your conclusion immediately here. That's the function f of x is the term now is discontinuous. See what I mean? Okay. It's discontinuous, and x equals -3. So we already came to an answer. But then for this specific problem right here, allow me to bring in another alternative. So I don't mean to waste your time repeating the problem right here, but I just want to point out some scenario. Because like I said earlier, that's requirement number 1 and requirement number 2, right? You can, the order 1 and 2 there is not a strict order. So who knows, sometimes, and among you guys, who knows, some of you favors doing limits fast. You see what I'm saying now? So in case you're starting out with a limit problem, as your requirement number 1, for example, right? You're doing the limits, right? The x squared minus 9 over x plus 3, right? And then x coming to the negative 3 being the limit point. So doing this limit right here, remember, because if you're starting out completely and focusing your mind to this problem simply as a limit problem, then we do not substitute it, then that means what? You can see that limit in the denominator will give a 0, right? So we have to do a little algebra beforehand. See what I'm saying? Now this is related to the material that we've learned in the previous lectures. And so in that case right here, we need to do some algebra. We need to factor out the numerator here, making it x minus 3 times x plus 3, right? And then do the divided by x plus 3 in the denominator. You guys follow me on that? Simply because I realized immediately that if we take that limit loss to the denominator, we're going to run into that limit going to a 0. So we can't directly use a limit loss yet. So we have to work around and bring out the limits problem down to a safe zone where I've been calling it like that. So x plus 3 cancel out, and that turns into limits of limits of the function x minus 3, but x get close to negative 3. So this here turns out to be having a finite limit, right? Finite existing limit here. So we're looking at minus 3, right? I mean, I'm skipping one little step through here, but you guys understand what I'm talking about. So we'll come to minus 3, subtract 3, okay? And then that's minus 6. Now, so it's a finite limit, okay? We put a check there. So that means if you started out as a limits problem fast, check for the limit and it turns successful, then that means don't stop right there. You have to advance to the next one. Am I making sense? So the next remaining one before that third one right there, you gotta check for the function's definition. Here it shows undefined. Am I making sense? So just be patient with these. Sometimes it's just depending on your style. Sometimes it depends on your style, how you start it out, right? And then you may start out with something successful fast. Then that means what? If you see one thing successful, that doesn't mean you stop right there and make your conclusion. You got to go on to the next one. See what I mean? The reason I put the next 3 here is because there was some step I didn't write down. I was a little lazy, but it was limit of the first term minus limit of the constant term here. See, remember that? Okay. And so now that here, we're not letting x equals negative 3, we only let x get close to negative 3. So limit laws allow me to say that, hey, this limit come out being negative 3. The limit here being a 3, a constant. And that's why I can go ahead and advance to negative 6. And see, the negative 6 here is not because we substituted negative 3 in and get 6, but because we let x get close to negative 3. And so the function turns into that behavior, get close, vertically close to negative 6. That's the reason now, okay? So, but now back to my main point I want to say. So then in that case, if one step turns out successful, then you still need to advance to the next step. And now, oops, recognizing that the second requirement, right? The definition requirement fails here, then you can just stop right there. You don't need to advance to the third step. And you say that f of x, right? Well, it fails right here, so f of x is discontinuous. At x equals negative 3. So how about f of x is defined to be as a piecewise function. How about x squared for x less than or equal to 0, and then minus x plus 2 for x greater than or equal to 0. So here's our function, right? And then, yes, that breaking point right here, that breaking line right here is what we want to consider for continuity. We want to find out if this function is continuous at this given point, x equals 0. All right, so let's get into it. So, well, it's just me. I'm more. It's my habit. I start out with checking for the definition first, right? Being defined or undefined. So, the function value at 0. That's to be step 1, right? Do we have a value here? Can we successfully calculate a value, the outputs for f of 0? Yeah. If so, what's the final output here for that? f(0), right? Because when x equals to 0, the requirement of your function says when x equals to 0 or less than 0, we take that piece, right? So 0 square, see, let's do this, okay? This is the input, 0 square, that's the function right there, so that comes out 0. So we have, so it's defined. It's defined, right? So we check on that. But that means we don't stop here and make some brush conclusion, right? We go on to the next one here. So let's now take the limits. So we want to take the limits for this function as x gets close to 0, generally from both sides. But this is where problems started right there. You guys see why? Because we have a piecewise function and being broken up right around x equals 0 right here, right? But we've had examples in the past when we learn about limits, right? When we primarily focus studying about limits earlier. So, what do we do in a situation like this? We have to tear it down to one separate limits coming to 0 from the left-hand side on this function. See what I mean? Right? And coming from the left-hand side mean all of the value for x that we get close to 0, those are all less than 0, right? So that means it's according to the piecewise definition there, we are instructed to use the x squared piece. You guys follow me on that? Okay, and then we take the limits when we're letting x come close to 0, but those values for x are all less than 0, right? Coming from the left-hand side. Right? So now we can use the basic limit laws here. So that is the same as limits as x gets close to 0 from the left on just a function x, and we raise it to the power. We had a limit law for that. Okay? And this comes out being what? 0. All good? Okay. But then that's only the left-hand side limits, so we need to do it again from the right-hand side for the same function. But this time looking at the x values coming close to 0 from the right-hand side, that means those x values we're approaching, they gotta be to the right-hand side or greater than 0, right? So here the piecewise function is instructing us to use the minus x plus 2 piece for here. Okay? And then we let it get close to 0 from the right-hand side. This now gives me, see, limit laws again says I can do one separate limit on the minus x term. Okay? X to 0 and plus the limit for 2 as the constants as we let x gets close to 0 to the right-hand side. Okay? So something like this, and you can see you can immediately realize that the negative sign here is just simply a -1 coefficient, right? So it's the same as minus the limit of x when x comes to 0 to the right-hand side. And then plus, now that constant term right here becomes constants, right? According to the limit law we've learned. And so in my next step right here, what do I have? Now when x comes to 0, that's a 0, right? So it's minus 0 plus 2. So you do have the right-hand side come to some limits. The left-hand side came to some limits as well. But do these agree? They don't, right? So that means the limits for this function, when x generally comes to 0 on both sides, what do you say about this limit? It does not exist, right? B and E right here. See what I mean? So this is immediately right there, that's where it fails the requirement number 2, right? The limit did not come out being a finite value, instead it came out does not exist, right? And so for that reason, now our final conclusion about this function. So f of x, right, leads to saying that f of x is discontinuous. Discontinuous at x equals 0. That's another problem we're doing. Yeah. Right. Then I still want to mention one more case with this. So think about another function. Piecewise definition again. How about sine of x over x? Or when x is other than 0, and then it equals 2 when x equals 0. And then we want to find out whether this function is continuous at x equals 0. Go ahead and spend some time writing it down. All right. So to tackle down on this problem, once again, if you're substituting x equals 0, right? into the function. What do we have? Is the function defined at that value? Yeah? What do you say? What's the output? 2. Right? See, that's why it has a definition, right? It says, hey, we define that when x equals 0, the output is 2. See, that's also some purpose of having piecewise function like that. Right? So yes, the function is defined. It has a value that came out. Okay? And then we check the limit. But just because it has one requirement is not enough, right? You're gonna have to check the limit. So the limit for this function, when x gets close to 0. Now remember, see, this is why I've been emphasizing it. Doing a limit problem is not the same as substituting it, right? Because why? When you're doing this, like you're only getting close to 0, but you will not be at 0. You will not take x equals 0, substituting it in. So that means, truthfully speaking, the limit problem here is done on this piece of the function. Am I making sense? You guys see that there? Because we're not substituting x equals 0 into the function. So the piecewise function here says, if you're substituting it, you gotta use this piece. But now, and when you're anywhere aside from that, right? When you're anywhere away from that, then you gotta use this piece here. And that's what limit is all about. Limit will never be at x equals 0, right? For this problem. So you guys following what I'm arguing right there? And that's why I'm using this piece. Right? And then x get close to 0. Yeah? So, I don't need you to do any algebra or any advanced stuff, but does that look familiar? The sine of x over x. The sine of x over x. It wasn't too long ago. Yes?
It's a special limit, right?
It's among your special limits. You know what I'm saying? Now, do you remember what that special limit is? You guys derived it on your own. One. Okay. So that was the one. That one we didn't really do any algebra. We got to use a table of values before it, right? And then we came to that conclusion right there. Okay. So we had a limit existing and being a finite. We passed that second requirement. But now here comes the danger. So we got both requirements fulfilled, but now observing requirements number 1 and requirements number 2. Let's come to the third requirement. Do these equal? The limit of the function when x comes to 0 and the function value at 0, do these come to equal? They don't, right? So clearly speaking, we can just write it down in one statement. The limit is not the same with the function value. See what I'm saying? So requirement number 3 fails right here. That's why we can ultimately make that conclusion. The function f of x, therefore, right, is continuous. Okay. And it's discontinuous at x equals 0. Okay. Sometimes we fail requirement number 1, sometimes we fail requirement number 2, right? Sometimes we fail the third requirement. See what I'm saying? Okay. So as long as we fail one requirement, right, our function fails to be continuous, and we have to say it's discontinuous. See what I'm saying? Okay. So that's the kind of problem where you guys have to do some math. What about when you're given pictures? Just because a lot of times your function is given just simply as a graph. Okay, so why don't you guys, once the screen is completely down, why don't you guys take a quick photo shot of that picture right there? If you need to, I can bring it a little bit closer on screen right there. All right, so have a photo shot of that. So wait for me to step out. And then we will depend on that graph, right, to consider, to look at, to decide continuity. Okay, so go ahead and have a Photoshop again. All right. And then on your own time at home, promise me to make a duplicate of that graph, right? Doesn't have to be precise, but put a picture of that on your note here. Because right now we just depend on that. We're going to just depend on that picture and then put it on our problem. All right. So let's call this number 2. This example number 2 right there. This is example 2. But you see the way how it's worded is a little awkward, and that's why I want you to get into this, because your assignment will be kind of, your web-based assignments will be kind of looking like that, right? But the graph is given, so we want to find out and right around that value x equals -1 right there, right? Right around that value, we want to determine which one of the, see, these are the 3 requirements to decide the continuity, right? At x equals 1. I mean -1, Okay, these are the three requirements, and the problem purposely mixed up the order all over, right? Shuffle the order all over here. But out of the three requirements, which one is the one that fails? That's why the wording is saying determine which one of the following rules, right, for continuity is violated. Am I making sense? Okay, so these are the requirements. If you're looking a little more closely, these are the requirements that came straight out from our definition of continuity. It's right here, right? But then the problem on the board you're seeing there is completely shuffling it, right? Put it all in shuffled order like that. But we need to identify which one is the one that made this function fails being continuous. Or in other words, which one is the one that's violated. Okay, so what do you see? Can we calculate the function value at x equals -1 or a in this problem? Yeah, we can, right? Because that's a solid point. See what I'm saying? So sure we can. So this is not violated, right? The function being defined, that's not violated. See what I'm saying? No? Okay. Now, and then usually the next step is we check for the limits, right? If the function's definition is defined, right? The function is defined, and we check for limits. Does the limit exist? This time the limit doesn't, right? One side goes one way, the other side goes the other way, like that, right? So limits. So the statement says the limit for f of x exists, but that's where it's a lie, like that, right? That's where it's a violation. See what I'm saying now? And so, like I've been expressing, once we recognize one violation, we don't need to move on to the next one, right? So we can just, and we select the one that's more primary. So here, right? I'm gonna select this one. Now, of course, because this one fails, of course the other one fails. But this one now I see that's more like the higher priority in terms of the reason, right? You see what I'm saying now? Because having that one fails, it will consequently make this fail. So we choose the one that has higher priority. So that's the one that making it violate like that. See what I mean? Okay. And so the way how your web-based assignments will work, right? Once you hit the correct answer, it's gonna mark you green for that, right? But that's the idea of how you're working with a problem like that. Okay, and so back at this point on my board right here, we're close to wrapping this up. And so we've been looking at continuous at one single point. So now you had a concern earlier because the idea now the graph is a lot more than just one point, right? So now we come to a definition that says a function f of x is said to be continuous on its domain. Okay? Meaning the function can have because it has a long domain, right? That's why it's long, it's go up and down, whatever, but it has some spreading, some horizontal spreading, right? So I'm saying a function is said to be continuous on its domain. Right? If it is continuous at every x value, underline that. Yeah, so if it's continuous at every x value in its domain. So there you go. So now back in that picture I brought up earlier, one graphic that, right, it goes through a lot of points. So if you want to say that this function is continuous entirely or continuous in its domain right here, the real philosophy is we have to prove that it's continuous here, it's continuous there, it's continuous there, it's continuous on every point on that graph. See what I'm saying now? But of course, for this level, we're just starting to get into it. I'm not going to make you guys do that kind of work, okay? That wait for some real advanced calculus class, okay? I mean, there's still a much higher calculus class. They still call it calculus class, but you guys pull every single thing out and prove that from the scratch, from the top, from the ground level, and proving it up, okay? We're not doing that here. We're just sticking with the more practical stuff here. But so now, that's just a definition to show you guys, but I'm not going to really make you guys prove any function to be continuous at every point, because that means a lot of work, right? It's infinite amount of work here. But so here's the thing. You've been familiar with those polynomials, right? From your pre-calc days again? See, so polynomials, and see, like I said, again, the loose thing in this class is that we never formally prove this. But we have been learning from past courses that polynomials are continuous everywhere. Can we make sense? Okay, so I put a check here means the polynomials past this definition. Polynomials are continuous everywhere on its domain. Okay. That's one of them. Okay. So quick scratch word, think about the x squared minus 2x plus 3. I brought up among the examples we've done earlier. This was a polynomial. So needless to say, whatever point I gave, right? Earlier in the example, I was doing x equals 1 as being the checkpoint, right? But it should have been also passing continuous and everywhere else. Okay? So that's the idea with the polynomials. You guys also learned about the rational functions back in your pre-calc 1 days, right? Those are, you have a polynomial divided by a polynomial. So rational functions are also continuous everywhere. It sounds a little dangerous, right? Everywhere except, there's the exceptions, right? Except the zeros, right? The denominator. Remember those? So the rationals are indeed continuous everywhere except the zeros in the denominator. That's just a little bit of a fancy way of saying it, but the truth is, for rationals, we always exclude out those are zeros in the denominator anyway, because the domain is only concerned any of those values except these. So that's why people can also say that rationals are continuous everywhere. See what I'm saying there? Okay. So aside from that, a couple of special trait functions. We learned about the sine of x and the cosine of x. Right? These guys are truly continuous everywhere. You have seen the sign of the wave for sine of x and the wave for cosine of x, right? And you can just waving those all day without lifting your pencil. See what I'm saying? That, right? So those two fundamental trait functions, they are continuous everywhere. Aside from that, we've got the exponential, right? Like the one like this, right? They should be continuous everywhere, right? So something like that, yes, also everywhere. And then your logarithms. Logarithm here. For the logarithms, the graph looks like this for the most standard ones, right? And so these guys are here. Yes, it's past continuous everywhere. Be careful, everywhere in its domain. See what I mean? Right? It's the domain for a logarithm is only anywhere that's greater than 0. Right? Not even x equals 0. Okay. All right, so let's continue with continuity here. So we cover essentially a big part of understanding for the continuity, but let's push into some further understanding. And so by last lecture, I was able to introduce those familiar functions like the polynomials, right? The rational, the trait functions, and the exponential, and log. Those are all continuous throughout their domain. So that means we have an impact here. So now think of it this way. Let's say, for example, you haven't, and I believe I mentioned it, but it wasn't too deeply yet. So think about we have a trait function, right? Sine of x, and we're letting x approaching some limit points, right? And so that means by doing this now, I reminded you that sine of x here is known to be a continuous function throughout its domain. So that means now taking sine, a lot of times taking limits of a sine function, right, or a trait function in general as x getting close to a value, that essentially means we can just simply substitute that limit point into the function here. So we are allowed to do this because we know now that our function here is a continuous function. Okay, and that's the idea. And so I've been yelling out loud since the beginning of our limits day that, hey, you do not substitute it in because at those times we don't know whether the function is continuous. But now on these, the point now is that, and this is only demonstrating the idea, but the point is once we know that our function is a continuous function, and taking the limit can be done simply as just substituting in the limit point values you get. Okay? So just like that, like the e to the x, right? then you're taking limits, right? When x goes to 0, for example, okay? Or well, let's take that to a generally a some limit point that doesn't necessarily have to be 0. And so that means now doing this, now once again, I know that it was pre-proven that e to the x, the exponential here is continuous. And so that means we can just do that e to the value a then. Right? We're substituting the limit point. So now we're officially allowed it to do substituting it because at a lot of these places here, a lot of these functions we're looking at, they are continuous. See what I'm saying? No? All right. And so in that way, let me bring in another example to kind of let you be comfortable with that. So at this point, you have to be extremely careful in the sense that some problems you are allowed to do, like the direct substituting in, but then you're still aware some problems you still have to strictly apply the basic limit laws. Because things don't always work out like so smoothly in one way. So let me bring in an example. So example 3 we've done, example 2 we've done from last lecture was the one with the graph, and you guys determine continuity based on the graph, right? So here, continuing with that. Let's look at example 3 here. So here we want to formally find the limits or evaluate limits. Okay, take limits to 0 here. So now the function itself right here, I do not know whether it's continuous. It's risky, right? The function itself, the whole thing right here, even though each one of these elements is continuous, the cosine of x individually is continuous, the e to the x individually is continuous, each little element, but the whole function right here, especially we got the denominator here, so when we're unsure, let's just strictly follow the limit laws, okay? So now I'm talking about, we're still going to do the limit laws as usual. Okay, limits when x gets close to 0, right, for x squared minus cosine of x, and then divided by limit of as x goes to 0 for e to the x minus 3. You guys all with me right there? So once again, the entire reason that I still strictly apply the basic limit laws or the limit laws in general for this problem to start out, because I was unsure whether our function here is entirely continuous. Okay, but then, so now the next step right here, we can save ourselves a little bit. So the limit laws allows us to separate it down to little terms, right? Limits for x squared as one term, and then subtracting the limits for the cosine of x. Okay, so x goes to 0. And then the same way right here, the two separate terms right here, we can do one separate limit for e to the x, and one separate limit for 3. See what I'm doing that? Okay. But now when it comes to this point right here, then each of our little individual function here is a continuous function. Say for example, the x squared, right, belongs to the polynomial class of functions. Yeah. So getting the limits to 0 is the same as just 0 squared. You see how I can just now easily substitute it in right there? We can bypass some of the the basic laws now, because we know that the polynomial is continuous. So going to a limit point gets me to simply substituting in that limit point value. In the same way with the cosine here. So cosine of x is continuous, right? Known to be continuous. So as we take limits going to 0 over here, we can just simply do cosine of 0. That allows that opens up more channel for us to do the calculation. And we'll be dividing. And then so here, as x gets close to 0, right? Not e to the 0 over here, we can easily substitute it in, as e to the x now is continuous. So we're officially allowed it to substitute it in. Okay? And then I'm subtracting, so it's a limit of the constant 3. Just like that, right? And so now our calculation comes out. Okay, so it's a 0 minus, so cosine of 0 is 1. Okay? So minus 1 on top, right? Because that's, needless to say, it's 0 now. So minus 1 divided by, okay, e to the 0 is 1, right? Minus 3, right? So now our answer comes out being positive 1/2, right? You guys all agree with that? So we still have to carry, see, part of it, I still have to do some basic limit logic, but in the end, when it comes to these elementary, when we broke it down to these elementary functions right here, we can speed up the process right here by simply substituting in the values. Right? So that's the whole usefulness of verifying that these functions from long ago that we know, right, they are continuous. And now we can treat them as simply taking the limits, simply done as a substituting in values for that. But remember, only work on continuous function, okay? And a lot of times it's critical at those values where there are those limit points that happens to fall into the critical places where your function fails to be continuous. That's where you have to strictly apply basic limit laws. Okay. All right. So now at this point right here, we will come to a huge. For us here, I'll call it a remark, but it was a theorem. It was proven formally as a theorem, but. Here I only want to treat that as a remark, something for you guys to pay close attention to, okay? And then, because I don't want to make it too formal, and then keep this with you, and then by the time that you arrive at either count 2 or even in count 3 level right here, this understanding will come back and become extremely beneficial, okay? But here's the thing. So it was a theorem. It was a theorem. Okay? It was a theorem that proven by mathematicians from earlier in our time here. But if the function f of x, right, is known to be continuous, so now just the short-term continuous without indicating the point, right, we're talking about it's continuous throughout its entire domain. Okay? So if f of x is continuous, not only at one point, okay, like I said, I emphasize that now we're saying continuous, it means like it's cosine of x, continuous throughout its own domain like that. So if f of x is continuous and further, right, the g of x is some function. G of x is some function. We don't necessarily know that it's continuous, but if we take the limit for some g of x, as x gets close to some arbitrary limit point here, and that limit there is a finite existing limit. So a lot of time, because we don't always want to write down every single thing in word, but when you see limits equals to a value like this, right, an indicated value, it means that behind the scene people intended to say that the limit comes to a finite value, right, being a particular value like that. So if we have these two conditions satisfied, then we can do, then the following is true right here. Now, you guys have seen from your pre-calculus days that we have composite functions, right? Remember that idea like that? So some function going into another one. That's why we call it composite idea. Composite function. So if you have a composite function that f composite of g, right, or in the way how it's written right now, that g is going inside of your f right here. So the order of operation is like that. We take g inside of f, and then the overall function, we take the limits. So this limit, x getting close to a on this composite function. That limit there can be done. Okay? I'm saying that. Now, if we satisfy these two requirements, then doing this limit, you can be done as the same as take the limit of the g of x inside. Take the limit of the g of x inside individually. Okay? And then whatever that, see, because eventually that limit will come out being L, right, as required here. Then we can just simply substitute the L value into your function f. You guys follow me right there? Or in other words, it just simply means it's the function value at L. Because we know that f of x is a continuous function. And actually, I lied a little bit earlier about saying that you keep this all the way to count 3 to see that. But actually, somewhere at the end of the quarter here, we will learn and we will have to make use of this information. It just sadly, we don't have some direct applications right now. Okay, but then when we come to somewhere near maybe the last couple of weeks of the quarter, like there will be that kind of problem where you need to utilize this understanding. You guys agree on that? Okay, and so let's keep that there for now. The last thing about continuity I want to mention. No, it's more about the different applications of continuity, the usefulness of knowing if your function is continuous. Earlier lectures, mostly we focus on, hey, what is continuity all about? But now once we know a function is continuous, we want to look for further usefulness of that. Oh, the board is better today. Let me introduce what's so-called the intermediates. Okay, so it's still a subtopic, under the continuity. So continuity is one big topic right here. And along the way, as usefulness of understanding about continuity, we're looking at the intermediates. intermediate value theorem. Right? We gotta learn about this intermediate value theorem after you've learned about the continuity of a function, and at least how to tell if a function is continuous. Now, this intermediate value theorem, the I, the V, and the T right there, yes, a lot of time people refer to that as the IVT right there. It's a shorthand, it's just a short way people are referring to it. It means the intermediate value theorem. It's quite famous, quite popular among the calculus students. Okay, so leave me some good amount of paper space there, but allow me to do some demonstration problem before we get into the idea of that. Okay. So let's say that I'm just demonstrating with a graphical explanation right here. So let's say we have a function, right? Function going up and down. Well, I'm saying a function nowadays, and you guys at this level, you should be well fluent enough to see that any function that can have a graph, right? And then the graph here can be waving up and down and all of that. So let's start out with the function here. Okay, is continuous. That's why I was drawing at least the part I was drawing on the board here was a smooth curve. I didn't need to lift the pencil, right? I only lift the pencil when I decided to stop drawing the graph. So there's your y-axis, x-axis, your function is here. Okay? But then the idea now that in the function I am going to, and it's famously it's gotta be a continuous function. And then in that function, on this function right here, I am going to restrict that down to a certain interval. So let's say it's just the way it is, and we're all familiar with that. Right? Any function, instead of letting it flow all the way through, right, we can just purposely restrict that into, see, there's a starting on the x-axis. The starting of our interval is x equals a, and then we stop our graph, right, at x equals b. See what I mean? Right? So x equals a is where we start on this interval, right? So we got a function, and then that function we only need to consider that function in between, somewhere inside of that interval from x equals a to x equals b. Sounds good? Further, let's look at, see the way how I drew the graph here. I purposely point out that case here. The way how I drew the graph is that let's look at those intervals where the starting point and the ending point gives a different f of, see this height right here, this vertical height, this vertical value right here, even though negative, right? But it's a function value. So this much right here is f of a. See what I'm saying? No? And then this other vertical value right here, that's f of b. So what I notice now is that in the way how I'm seeing it, the function value at b, this height right here is different, right? I drew it in a way that the ending point is different with the starting point, okay? The vertical value, the output of your function at b is different with the output of your function at a. So that's another requirement again. So we want to put ourselves in, we want to consider looking for ourselves into a function being continuous further, right? We're looking at some interval where it has, left end gives an output being different with the output on the right end. Okay, just being different. I'm not saying that f of b has to be higher. Well, in the case I'm drawing right here, f of b is higher, right? But the point is just, it could be a different one. Like, say it could be f of a is here, right? And then you draw your graph and f of b is here. See what I'm saying? Now, f b, a and b. Okay, so f of b, a, and f of b is right here, right? But it's still falling into what we're considering here, that f of a is different with f of b. You guys follow what I'm saying now? So what I've been emphasizing, the reason I keep addressing that f of a needs to be different with f of b is because if you're putting f of a and f of b together on the y-axis, right, and we form an interval as well. You see what I'm saying now? On the x-axis, we have an interval going from a to b, right? And then on the y-axis, we also have an interval. And depending on whoever is the larger value, right, that's when it's going to be the lower. The larger value stays on top and the lower value stays at the bottom. But my point is, more importantly, well, generally we have an interval on the y value as well, on the y-axis as well. See that now? So now inside of that interval, so after talking about the couple basic requirements there, so now inside that vertical interval on the y-axis, simply pick any L value, simply pick any L value. if L is inside of your interval, well, in my picture right here, FA is lower, right? So allow me to draw it like that. Inside of the interval from FA, right, to FB, you guys following? It's the interval on the vertical axis. Inside of that, you pick, by the way, in case I haven't used this symbol before, you guys see a little, kind of like a sideways cup right there with a little dash in between? Right? This symbol, if you're already familiar, that's good, but in case you haven't seen it, it means in. Well, it's just us, the mathematicians, we love replacing the written language with symbols and all that. And so this is actually a statement. It says for any L value, right, falling in between, right, or inside of this interval. That's what this symbol is. Okay, see, so much wording, so much verbally saying it out, but it's just one symbolic statement right there. For any L value being inside of this interval, then we can guarantee that this is one thing that can be guaranteed. We know for sure. I know. See the graph. You pick any L in between, and you draw that horizontal flat line right here. Don't you notice that this horizontal line will eventually cross the graph for sure at some point? See that there? Okay, it will cross the graph. Because see, the first thing is because the graph itself is continuous. Okay, and in the way how we drew it, it produced a vertical interval for outputs on the y-axis. So now picking any L value, right? Picking another L value. See? Drawing the horizontal line, right? That L value will cross the graph at least one point. You see what I'm saying? No? That's what's guaranteed by the intermediate value theorem. Okay? It's a truth that it was brought up by the earlier generation mathematicians like that. And so that means what? Okay? So it must be true, right? It must be true that, and so the line crossing, but in a more formal math, it means like this. It means that the functions, right? The function f of x right here must equal L. It's true that the function must equal L. The function must equal L for some value. For some value x equals c. Some value x equals c that's falls inside of the interval from A to B. Right? So I'm talking about, or in other words, say graphically speaking, that horizontal line L, right? That's located anywhere in that inside of that vertical interval. That horizontal line L has to cross the graph at some value in between A and B. Right? The A and B is the interval on the x-axis. All right, so now formally writing it down right here, then I'm going to start out with L function. Yes, L function is required to be a continuous function. So then f of x, right, be a function. Right? Then required that continuous on the interval from A to B. Okay, that's the first requirement. Like I said, the function, the way how we drew my graph here, it got to be like one smooth curve at least inside of this interval from A to B. Right? I got to draw my graph without lifting the pencil. Right? So let f of x be a function that's continuous on the interval. And further, I want to ensure that f of A is some value different with f of B. This is what I was saying earlier. So these are the two requirements being stated in that one statement right there. So anytime you're considering a function that meets these two requirements, being continuous on an interval and having those two endpoints be different, right? Then the following result is true here. You see how exactly did I worded that. So in that case, it's true that there exists, right? There exists a value x equals c that is inside of the interval from A to B. Okay? There must exist. So this is a guarantee, right? The theorem guarantees that there exists. There will be. You can find a value x a value x. We call that, hey, x equals c, right? But that c falls inside of your interval from A to B. Satisfying. satisfying f of c equals L, for L is a value in between A and B. To be precise here, why don't you guys add this word here? Or keep pushing around a little bit, but see, for L, it's more precise to say for every L. So I'm talking about not just only for L, for every L. You pick any L value, right? For every L between the two vertical outputs right here. Pick any two, pick any L. You can, the theorem exists. The theorem guarantees that you will be able to find a value X in between A and B that meets this requirement. Right? That meets that condition of that. Okay? So now it's not just about we write it down and we try to cram through it, memorize it or whatsoever. Right? The better idea is let's see how useful this can be, because right now that's just the demonstration. Now let me bring in a better, good application for this. Let's say we have, you guys at this point learned solving quite some good number of equations, right? Like say there are those quadratic equations and linear equations. You guys are supposedly fluent, right? Okay, but so let me bring in something like this. X squared plus 5x plus 8 equals 0. It's an equation, right? Quadratic equation, familiar? Because it's got the square term in there and it's got the linear term in the middle, right? It's got the constant term, but most importantly, it's quadratic because it's got that square. But so, solving this one here, you're gonna roll immediately into, do the factoring process or the quadratic formula and whatsoever, right? But let's say, no, I don't need any of that. I don't need any of that. No, that's not solving it. That's not solving it. So here's the instruction. Think about it. I want to bring up a problem like this. How about without solving? Because how you have been trained before is that when you are given an equation, you just roll into your method tray and then solve for it to find the x values that make the left-hand side equal to the right value, the value on the right-hand side. You guys agree? You still remember that we have 3 methods again, right? To complete the square or whatever, right? On this specific family right here. But now my instruction here is, how about you guys don't solve without solving? That's the idea again. You don't need to solve. You don't need to bring out your quadratic formula. Without solving, will this equation have a solution? Okay? See, it's some way that I want to determine for me. Will this equation have a solution inside of the interval? So let me, all right, spend some time, copy down the wording of the question like that to really understand the intention. All right, so I have the problem written down so far. And it's not even an example yet, it's just some demonstrations I want to bring in to show you how useful this IVT is, this intermediate value theorem can do for you. Okay, so think of it. What's your, naively enough, when you see an equation, right, x squared plus 5x plus 8, right, equals 0 over here, you're going to start thinking immediately into, because the question, the main core of the question is asking you, will this equation, right, will this equation have a solution, right, inside of the interval from 0 to 2? So to answer this question more naturally, or I'm saying naively, right? Because we're gonna go with whatever the method you solve for that, right? And so we're looking for well, let's stay with the quadratic formula of minus b plus minus square root of b squared minus 4ac. You see what I mean? Okay. Over 2a, right? And so that brings me into, see, minus 5, right? Plus or minus, you guys still all comfortable with the quadratic formula, right? I'm not saying it's the fastest route, but it always guarantees you arrive at some solution. So the square root and b squared here is going to be a 25, right? Minus 4 times, so minus 32 over here. Over 2. And then you're going to end up with complex number, because you notice there's going to be a negative right here. So from some of your pre-calculus days, or let me write it down like this: -5 plus or minus square root of a -7, right? And then over 2. That's where the problem starts again. Okay? When you solve something like this. Now, if it's just strictly a pre-calculus course, right? Before getting to the complex numbers right there, which by the time you guys arrive at calculus, not too many people familiar with complex numbers yet. So usually, or majority of time, the solution like this. I mean, when you come to this calculation right here, your equation here is set to have no solution. See what I'm saying now? Your equation is set to have no solutions, right? And so of course, if we went this route, right? If we went this route, what have we guaranteed? What have we just said right here? That means what? No solution means, hey, in this interval from 0 to 2, right? This equation will not have solution in that interval. Do you guys agree? Okay. But then so much work. Unfortunately, I'm going to have to say, hey, this is not the way I want you guys to do it. See what I'm saying? No, solving it, right? Solving it to answer whether you have found some x value inside of this interval is not the way, right? That's the idea right there. And of course, doing this one right here took some of your time watching me doing it, right? It takes time right there. That's the idea. So is there a better way? Is there a different way so that we don't even have to pull out these tools here that we've learned, right? But we can still guarantee if this equation here has a solution inside of that. See what I'm saying now? Okay, so here's the plan. So now it seems so much work, but I'm taking it out because that's not the solution I want. Okay? So you see on this board right here, that's why I have to emphasize this problem truly is asking you to determine that, but without solving, without doing the quadratic formula whatsoever. So here's the way how I'm seeing it. You have to understand another thing. Ultimately, anytime you solve an equation, right, and you're letting your let's say after you have pushed all of your terms to one side and leaving a 0 on the left-hand side, that means you can always define a function f of x to be that left-hand side expression or that one-side expression. So here, x squared plus 5x plus 8. You guys following? Okay. So this equation here means kind of like equation x squared plus 5x plus 8. It's just optional explanation for you. That equation here means you're trying to solve for f of x equals 0. Okay? Your teacher from the past courses should have also mentioned that, hey, solving an equation means we're trying to find a line where the graph crosses, right, with this specifically equals 0 right there on the right hand side. It means where we want the graph crosses with the x-axis, right? Because the 0 here means y value equals 0. You guys following me on that? Okay? Okay? Kind of got that reminded. Okay? And so in this case here, and we'll put that piece of understanding back to good usefulness. But now you got a function. That's just what I pointed out, right? From this equation, you can understand that our function here is x squared plus 5x plus 8. You see, we're talking about an interval, right? First of all, it's a quadratic, so f of x is continuous, isn't it? We've learned that straight out from our learning just earlier. Because being a polynomial, right? Polynomial is continuous, so at least I know that this function here is continuous on the interval from 0 to 2. So 0 to 2 is the interval of our main focus, right? That we want to pay attention to that interval. Just the problem is asking us to do so, right? Pay attention to that interval. So we know for sure that f of x is continuous on that interval. And further, one more thing. Right? Another bullet information right here. How about f of 2? What's the value for f of 2? Well, you can do the calculation, right? Substitute 2 into your function. Yes? So that makes a 4 here, right? And then a 10 here, right? And by the way, so the odds is 22, right? Did I do my math right? I make these silly arithmetic errors all the time. Yeah, make sure you guys do the work. Double check me, yeah? All right, and then f of 0, you see what I'm doing with these 2 and 0 like that? I'm substituting in the two endpoints of our interval, right, into the function. So f of 0 gives me what? That's a 0, right? Plus 8. So that means what, with the bullets, information number 2, I'm seeing that f of 2 is different value with the f of 0. See what I'm saying? That. Are we good with that? Okay. And so now think about on the vertical interval right here. Now see on these two values are on the vertical value on the y-axis right here, right? So this time I'm seeing that hey, the value L is actually equals 0 because you see this f of x right here. Think about your equation here means f of x equals 0, right? So let's say with that value L equals 0 right here, can there be, right? Can we find? So the illustration I'm seeing here is that your f of 2 and I'm about to draw some sketch version, but I'm not intending to draw the exact graph of the x squared plus 5x plus 8. Don't even judge me on that, okay? But the idea is, according to this information, f of 0 give me some 8, right? And then f of 2 give me some high point 22 up here. You guys see what I'm saying now? So from f of 8 to f of 2 right here, there's some kind of graph working in between, right? But see, I want f of x equals 0. I want f of x equals 0. Can that even be true right now? You see what I'm saying now? Because the L, so this is, I call it the L line right here, right? And the L line is not even in that interval. The L line is not even in between these two values. So now from that way right here, I can see that, okay? So L, right, is L equals 0, and we can see that L is not even in the interval between 8 and 22. These are the vertical output values together. You know what I'm saying, no? So that's why I'm saying that, hey, for sure, right? No solution in the interval from 0 to 2. You guys good with me on that? Okay? So we use the intermediate value 0 to answer this question right here by simply just bypassing completely the solving work with that. Right. All right, so now let's bring that into an actual example. Okay. So go ahead and spend some time writing it down. I did some demonstration earlier, so now we're going to really put that into an actual example. All right, so this example right here is very similar along the way with that demonstration problem I brought up earlier. See, in the demonstration problem, I was bringing in that wording that, hey, without solving, right, and with something like this, here's the intention, and this is the more practical situation right here. People give you an equation. But now think about it. Do you know how to solve this equation? Does anybody know? Because I don't know. I'm sure I don't know how to solve this thing right here. But if you know, that's super good for you. But see, the idea is, out of a very challenging equation like that, right? Which is, maybe a couple people know, the rest of the world don't know, right? Out of an equation like that, we still want to know, can there be a solution? Can there be an x value to satisfy this equation? Can there be a solution that's located inside of the interval -3 to -2 on the x-axis? See what I'm talking about? That's why, naturally when people see in this instruction, they will tend to solve the equation. And so as I said, maybe out of the whole world, a couple people know, right? And then the rest of the world don't know. I belong to the rest of the world where I don't know how to solve this thing, okay? If you know how to solve it, that's super good for you. But see, the idea now is that we don't need to directly solve it, right? So needless to say over here, without solving it, that's my explanation right there. Or for order to get to that main purpose, without solving it, we still want to find out, can there be a solution located inside of that interval on the x-axis? Okay, and so the work now falls out quite usual once you understand the main purpose of the problem. You can see that this equation here, we already had all the terms, right? All the non-zero terms pushed to one side, right? Namely the left-hand side over here, and then leaving the opposite side is 0. So I can just simply define a function f of x to be what? E to the x over 2, right? Minus e to the minus x over 2. You guys following what I'm doing there? And minus 2, right? So that's one function right there. Is it an exponential? Not quite. Is it a whatever function? I don't know. It's just some function out there, right? It's just some function out there. It's just way out of ordinary. This kind of function is not even any of those that we've been working with throughout our pre-calculus stage. But anyway, this function for sure I know one thing. This function here, the first bullet's point, f of x, I know for sure, see? At least each term here is a continuous function, right? Each term comes from a continuous function. You guys agree? because it's an e to the x, right? The e to the x over 2 is just simply an e to the 1/2 times x. So it's clearly that term is an exponential, so it's continuous. Sounds good? The other one, e to the minus x over 2, that next term right there, okay, is simply just e to the negative 1/2 coefficient times x. So it's another exponential function right here, which is just a coefficient with that x. You guys with me on that still? So it's continuous, constant function is continuous. And so simply adding or subtracting these terms right here will produce an overall function being continuous. We've learned this back into college algebra or pre-calculus, right? And so that's why now I can guarantee that f of x. See, you don't have to formally prove it. People will know. And of course, for instructors, we will give you functions that you can easily verify continuity right there. So f of x is continuous. Right? At least on that interval from -3 to -2. Because you know that this function is even continuous for all x values in the real domain. Yeah. So after that, my next thing I'm pushing into, so the next bullet point here, see? What's f of -3? This is the part where you can help me with the calculation right there. So f of -3, you see where I got the -3 from? The left end of our designated interval, right? I'm substituting that value into the function. So, of course, we're going to go with crazy decimals. Go ahead and help me out with that. And actually, I have a little typo right here in my work. Actually, this interval I gave out was the wrong one. Can you guys actually change this? Sorry. So much for that. I'll just take the interval from 0 to 2 to make things simpler. Sorry for that typo. Okay. So now I'm going to pick the first and the left hand. Right? The left hand is actually no, substituting 0 into your function. You got it. Should be a 1 minus 2. That should come out with a -2. You guys can double confirm that with me. All right. So agree with -2 on the x equals 0 right there. All right. So now we do it the same way. The next, the right-hand side interval value, so f of 2 right here, substituting that x equals 2, the right hand of our interval into the function. You're looking at e minus e to the -1, right, minus 2. When x equals 2, right, these cancel out, giving me an e to the first power, and e to the -1 power, and all of that. What's your quick answer right there? Okay, 0.35.
040.
Okay. Something like that, a lot longer. The point now is that, see, obviously, f of 2 is different with f of 0. You know what I'm saying, no? F of 2 is different with f of 0. And, you guys clear with that, right? And then, so now L is the value 0, because we can see this, once we define this right here, that means this. We have the equation here means we got f of x equals 0, right? So we can take that to be our L again. So L equals 0 is falling somewhere in between. So between these two values, one of them is negative, the other guy is being positive, right? So L is in between -2 and 0.3504 on the vertical axis here. You guys with me on that, right there? Okay. And so now, here's the thing. Now, since L is between that interval, and then the function is continuous in that interval, and then these two endpoint values are different from each other, right? Or you can say according to the intermediate value theorem, as long as your L is falling between the two vertical values right here, there will be a value C inside of that interval, guaranteeing that f of C equals L. You know what I'm saying? No? Okay. So that means what? That means on this equation right here, once we guarantee that L is inside the interval, right? The IVT guarantee, okay? There must be a value C inside of the interval from 0 to 2 right here, satisfying f of c equals 0. You know what I'm saying? No? And f of c equals 0 here means Or the last thing we can say, right? The equation, equation has a solution. Okay? Each side of the interval from 0 to 2. The statement will say right here. Okay? So we have answered that question. The answer here is really is a yes, right? There will be, there can be, and there definitely will be a solution in between 0 and 2.